Math 2312, lines, parallel and perpendicular lines. In class on Thursday, September 24th, which as of the filming of this video is yesterday, we quickly, not too quickly, but we reviewed lines and lots of things about them. We reviewed slope, we reviewed point slope form, slope intercept form. I mentioned general form, but I'm not too big on it. We talked about graphing the equation of a line. Well, given the equation of a line, sketching its graph, primarily by looking at the equation of the line in slope-intercept form, or converting it to slope-intercept form first if it wasn't, and then using the information contained in slope-intercept form to sketch the line. Namely, the y-intercept told us where on the y-axis to put a point, and the slope, when viewed as a ratio of rise over run, gave us two directions to go from that point, starting at the y-intercept, run according to whatever the run is, and then rise according to whatever the rise is, keeping in mind that a negative rise would go down instead of up, and then locating a second point to connect to the first point and sketch a line. We also talked about how to sketch general form using intercepts by taking advantage of the fact that if you are an intercept, then one of your coordinates must be 0. Specifically, if you're an x-intercept, meaning that you're a point on the x-axis, then your y-coordinate must be 0, and vice versa. If you're a y-intercept, meaning that you're a point on the y-axis, then your x-coordinate should be 0. That concept of locating intercepts by letting the other variable equal 0 is not limited to lines. It's always applicable for any equation that we're attempting to graph. So keep that in mind as it will show up again in the future. But there's one small thing that I did not get to yesterday in class that I do want to cover briefly for two reasons. Number one, there are points in calculus where you may need to know these two things. And number two, in the homework assignment that I created in Canvas, there are questions about these things. So I think for that reason alone, it's probably worth my time to make this video and worth your time to watch it. Specifically, that thing was about parallel and perpendicular lines. If this were a college algebra class or something prior to pre-calculus, I would develop these topics, but I'm considering this a review, so we're going to treat it just like that. I do want you to recall that slope measures the steepness of a line. It's amazing how many good math students either never think about that or were never told that in the first place. But that's all slope is. It's a measurement of the steepness of a line. So how can we use this to describe the relationship between the slopes of parallel lines? Well, if two lines are parallel, it basically means they have the same steepness. Technically, the definition of parallel is non-intersecting. In 2 dimensions, that's the definition of parallel. In 3 dimensions, it's a little more specific than that. But in 2 dimensions, two lines are parallel if they never intersect. So in terms of their steepness, they have to have the same steepness. If they didn't, at some point they would meet. So we can say that two non-vertical lines are parallel if their slopes are equal. And you may be wondering why I put the word non-vertical in there. Well, if a line's vertical, what's its slope? That's a trick question. If a line's vertical, the slope is undefined. I forgot which of these is my better black marker. So technically, we can't say that two vertical lines are parallel if their slopes are equal because they don't even have slopes to begin with. But if you have two vertical lines, they're still parallel. They're just parallel for a different reason. They don't intersect. Otherwise, we could also say that their slopes are equal as long as they're not vertical lines. Now, the perpendicular case is a little bit trickier to explain. And I'm debating whether, and I'll just do it. Well, first, let me just give you the review, because this is a review, but the teacher in me can't just say, here it is. I have to back it up a little bit. Two non-vertical lines, again, same reason, because a vertical line has no slope. Two non-vertical lines are perpendicular if their slopes are opposite, meaning one is positive and one is negative, so opposite in sign, and reciprocals, meaning that if you turn one of them upside down as a fraction, you get the other one. So you change the sign and you turn the fraction upside down. Now this is equivalent to saying that the product of their slopes is -1. Because if you have one slope, and to be generic, let's just call it A over B, then the opposite reciprocal would be you change the sign, so you would stick a negative in front of it, or if it already had a negative, you would remove it, and you reciprocate it, which means you turn the fraction upside down. So that's the visual way to see the two slopes are the slopes of two perpendicular lines. Let me try that sentence again. That's a visual way to see if two lines are perpendicular by examining their slopes. One's positive and one's negative, meaning they have opposite signs, and one is the reciprocal of the other, meaning that you turn the first fraction upside down, you get the second one. But algebraically speaking, if you multiply these as fractions, the a's would cancel, leaving a 1 on both sides of those fractions. The b's would cancel, and you have nothing but a bunch of 1s and a negative, so the product ends up being -1. So from an arithmetic perspective, you can check to see if the slopes of two lines represent perpendicular lines if their product is -1. Personally, I prefer saying opposite reciprocal because that's a little bit more visually descriptive than saying that the product of their slopes is -1. Real quick, the reason opposite reciprocal is a thing for perpendicular lines is real easy to explain. I was never taught this. I just sat down one day as a teacher and said, all right, I know this is true, but is there an intuitive reason why? And there is. But in order to show it to you, I have to draw a couple of perpendicular lines, which I'm assuming everybody knows, two lines that meet at a 90-degree angle. By the way, perpendicular is not the opposite of parallel. The opposite of parallel is intercepting. But I digress. If we have two perpendicular lines and we want to look at their slopes, think about how you would measure the slope of the first line by drawing a run and a rise situation. So this would be the run, this would be the rise, and whatever they are, your first slope would be rise over run. Well, to get that perpendicular line, imagine taking these two lines, or rather imagine taking the first line, sticking a push pin right there, and then rotating it 90 degrees to get the other line. If you rotate this line 90 degrees and rotate the run and the rise with it, they would go up here. So what would the slope of the second line be? Well, the run rotates and lands here, and the rise rotates and lands up here. And if you notice, I put rise and run in quotes because when I rotate them 90 degrees, they trade places. What used to be the run is now going up, and I'm going to draw these arrows here to indicate the directions of the run and the rise before I rotate this picture, which means those arrows would rotate this way. So if you rotate this original line with its run and rise illustrated and rotate it 90 degrees counterclockwise, what used to be the run pointing to the right is now pointing up, and therefore is the rise. Which means when I calculate the slope, its rise is this guy. So rise over the run. Same thing with the original rise. The original rise, which pointed up, that was the vertical displacement. Upon rotating the quarter circle, is now pointing to the left. So it's a horizontal displacement. In other words, the rise becomes the run. So it moves to the bottom of the fraction. However, well, that justifies the reciprocal aspect. When you rotate this little triangle 90 degrees, the rise and the run essentially trade places. But where do we pick up this extra negative? Well, when you rotate it, somebody changes signs. Not the run. The original run was pointing to the right, that's a positive direction. Upon rotation, it's pointing up, that's still a positive direction. But the original rise, which pointed up, which is a positive direction, upon rotation is now pointing to the left, and that's a negative direction. So that guy picks up a negative sign because he changed whether he was going in the positive direction or the negative direction, and hence the opposite nature. So perpendicular lines have opposite reciprocal slopes because upon rotating this line with its run and rise, rotating it all 90 degrees, the run and the rise trade places, hence the reciprocal, and one of the two changes the signs of its direction. In this case, the rise used to be positive, but upon rotation, it now points in a negative direction. Now, do you need to remember that? Of course not. But as a theoretical mathematician, I always like to justify why things are true, and that's a pretty good justification. There are some other ways to show that perpendicular lines have opposite reciprocal slopes, but I think that one is the most visually appealing. All right, let's get to the examples of the types of problems I want you to be able to do, which are namely finding equations of lines, although I can think of other contexts involving parallel and perpendicular. For the first example, let's find the equation of the line that is parallel to 3x plus 4y equals 7 and contains the point 12, 19. To be nitpicky, it should say that is parallel to the graph of 3x plus 4y equals 7, because this isn't a line, this is an equation. Its graph is a line, but we can assume that they're interchangeable for now. All right, so how do we find the equation of a line that is parallel to that and contains the points 12, 19? I didn't write it up here, but we're going to answer in slope-intercept form. You can pretty much assume that most lines' equations as answers to problems should be written in slope-intercept form because slope-intercept form is unique for a given line. Well, just like we said in class, if we're going to build the equation of a line, we need a recipe and its ingredients. You almost always start with point-slope form. So we need a point and a slope. We do have a point. Our point is 12, 19. In the context of slope-intercept form, we would call that x1, y1. The first x and the first y were given, which are the only x and the only y that were given. But in order to use point-slope form, we need a slope. Remember, point-slope form is no it's not. Point-slope form is y minus y1 equals m times x minus x1. So how do we get the slope? Well, by taking advantage of the fact that the line that we're looking for is parallel to 3x plus 4y equals 7. When you're writing equations of lines and you're given a parallel line, you can actually replace the phrase parallel to with has the same slope as. Now, you don't have to physically do this, but you could think of changing that phrase to has the same slope as. And now it reads the equation of the line that has the same slope as 3x plus 4y equals 7. Okay, well we need to find the slope of 3x plus 4y equals 7 and then use that slope. Now, what's the slope of 3x plus 4y equals 7? Well, it's not 3. A lot of people think y equals mx plus b, the slope is in front of the x. Well, yeah, if the equation starts y equals, which this one doesn't. So to get the slope out of there, we should probably convert it to slope-intercept form, then look in front of the x. To convert it to slope-intercept form, and recall that slope-intercept form is y equals mx plus b, we simply have to solve for y. And we can do it in two moves. We can solve for y by taking this 3x and subtracting it to the other side, which would give us 4y equals negative 3x plus 7. And then divide everything by 4, which would give us y equals negative 3/4 x plus 7/4. And at that point, the slope is in front of the x, and the slope is negative 3/4. Now, some of you are savvy enough that you can look at this equation in general form and think about moving things around like I just did, and see that the slope is going to be negative 3/4. However, on a test, it's worth your time to write the steps. It lessens the chance of making a mistake and gives me more of an opportunity to award partial credit if something goes wrong. All right, so do we have everything that we need? Well, yeah, we have a point. The point is 12, 19, which means that x1 is 12 and y1 is 19. And the slope that we're going to use, or rather I should say the slope of this line, is negative 3/4. Therefore, our parallel slope, which I'm going to write as m subscripted with a pair of parallel lines, that's not an 11, that's a pair of parallel lines, the slope of the given line is negative 3/4. Therefore, the parallel slope is also negative 3/4, and that's the slope we're going to use. Now I have the necessary ingredients to build point-slope form, so let's build it. Y minus the y in the point that we're given, which was 19, is equal to the slope, which is negative 3/4, times x minus the given x coordinate, which was 12. We now have the equation except it's in point-slope form. Y minus 19 equals negative 3/4 times the quantity x minus 12. Since we do want slope-intercept form, we need to fix the things that are wrong with it. Namely, we need to eliminate the parentheses and isolate the y. Eliminating the parentheses is just a matter of distributing the slope. The fact that it's a negative 3/4 really shouldn't impede your progress. You may need to slow down a little, but you should get past it. Negative 3/4 times x is negative 3/4 x. And on the second half of the distribution, negative times negative is positive. And if you're still struggling with things like 3/4 times 12, please watch this. Any fraction times any whole number is easy because you can put the whole number over 1 and then multiply straight across. 3 times 12 is 36, 4 times 1 is 4. And then if the fraction reduces or flat out divides, do it. 36 divided by 4 is 9. Now, some of you are thinking, wait a minute, couldn't I have done this? 3/4 times 12 equals 4 goes into 12 3 times 3 is 9. Yes, of course you could. Sometimes you can reduce before you multiply. In fact, if you can reduce, you always have one or two options, before you multiply or after. Sometimes reducing is not an option, but multiplication always is. So my preference sometimes, when the numbers are small, go ahead and multiply it all out and then worry about reducing later. But if you can catch the reducing at the beginning, it actually makes the multiplication smaller with smaller values. So whichever way floats your boat. All right, so anyway, we're close to the slope-intercept form. All we have to do is isolate the y. So if we add 19 to both sides, that will give us a final answer of y equals negative 3/4 x. And then positive 9 and positive 19 is positive 28. There's our equation. All right. I do want to point out one thing. The equation that we were given, we needed its slope and nothing else. A question I often get is, what about this guy's y-intercept? Why didn't we use it? Because we didn't need it. The only thing we needed from this was its slope. Its y-intercept was completely irrelevant. Let's check out the other one. Find the equation of the line that is perpendicular to 3x plus 4y equals 7 and contains the point 12, 9. In other words, the exact same problem, I just changed the word parallel to perpendicular. Well, how would we do this one? I invite you to pause the video and see if you can get to the answer before I do. And we've done a lot of the dirty work already in the previous problem. If you were to analyze this from beginning to end, it would go something like this. We're going to build the equation using point-slope form. That's our pretty standard leaping off point for writing the equation of a line, which means we need a point and a slope. We have the point, we do not have a slope yet, but we're given information to find the slope. Just like up here where I changed the phrase as parallel to the phrase has the same slope as, the phrase is perpendicular to can also be translated to a different phrase. The phrase has the opposite reciprocal slope of. And again, you don't have to physically make this change, but you can mentally or verbally make it. Has the opposite reciprocal slope of, and now it reads, find the equation of the line that has the opposite reciprocal slope of 3x plus 4y is equal to 7. Okay, that's a little bit more descriptive. I need the opposite reciprocal slope of this. So I need this equation's slope and then take its opposite and reciprocal. Now from the work that we already did in the previous problem, we know that this line's slope is negative 3/4. But that's not the slope that we need. We need the opposite reciprocal slope of that. Therefore, the perpendicular slope, and I'm going to subscript the m with a perpendicular symbol. It looks like an upside down capital T, but that is the industry standard symbol for perpendicular. If the original line slope is negative 3/4, then the perpendicular slope I'll get by taking both the opposite and the reciprocal. The opposite would be positive since the original slope is negative. The reciprocal would be to turn the 3/4 upside down and make it 4/3. That's the slope we want to use. That's the opposite reciprocal slope of the given line. Okay, we have the slope that we want and we have a line. So we can start building point slope form, which is y minus the given y coordinate, which is still 19, equals the slope, and this time the slope we want is 4/3, times parentheses x minus the given x coordinate, which is still 12. And now we just have to push it to the end like we did before. Again, don't let the fraction throw you off. Actually, there's another way to think about 4/3 times 12. 4/3 is just 4 divided by 3. This is 4 divided by 3 times 12. But nobody said we had to do the division first. We could do 4 times 12 divided by 3. And nobody said we had to do the 4 times first. We could do 12 divided by 3 times 4. If you see that the denominator of a fraction will divide evenly into the number you're multiplying it into, I would do the division first, not with the 4, but with the 12. So when I see something like 4/3 times 12, what I think is 12 divided by 3 times 4, because I can do that in order. 12 divided by 3 is 4, 4 times 4 is 16. Marker's about to give out here. Now, if the mental approach to doing that is not in your wheelhouse, then don't. Write it over here, put the 12 over a 1, multiply to get 48 over 3, question whether 48 will divide by 3, it will, you get 16. Or, if you prefer the reduce first approach, 4/3 times 12, 3 goes into 12 4 times, which is the first thing I did mentally over there. 4 times 4 is still 16. I really don't care how you multiply your fractions. Just do it, because you're in pre-calculus and they're just fractions. We done? Nope, because we want slope-intercept form, and this isn't there yet. We're just one move away. Add 19 to both sides. And we get a final equation of y equals 4/3 x. Looks like plus 3. And again, you may be wondering, why do we not mess with any y-intercepts? Because the discussion about parallel and perpendicular has absolutely nothing to do with y-intercepts and everything to do with slopes. Well, almost. It is worth pointing out that two lines are parallel if they have the same slope, but they can't be the same line. Otherwise, they would not just intersect at a point, they'd intersect completely. So technically speaking, you would say that two lines are parallel if they have the same slope, but different y-intercepts, making them different lines. But in general, we don't worry about the y-intercepts being different. They typically end up being different anyway. In terms of calculations, it's all about slopes. The y-intercepts just kind of make an appearance at the end. And if you have a y-intercept at the beginning, don't really need it, because those equations were there to give us a slope. All right, so I just wanted to tie up that loose end about parallel and perpendicular lines. This is a longer video than I typically make, but this is the only video that I plan on making to wrap up what we talked about in class. So instead of putting out multiple small videos, I just thought one longer video would be sufficient. If you have any questions, please do not hesitate to contact me. The homework for this section about lines is in Canvas. It is under quizzes. It simply says lines. It is due midnight Tuesday. That's the next day I see you. Tuesday, September the 29th, I believe. It has 20 questions, some of which involve this, and you have unlimited attempts. But please contact me if you have any questions.